Hello. In this lecture, we're going to talk about electrophilic aromatic substitution, and in particular, we want to discuss how substituents can have an effect on the reaction. So just sort of recap where we left off. We were talking about reactions of arenes and sort of introducing the concept of EAS. And what we saw was that benzene is very distinct from alkenes in that it's largely unreactive. One of the reasons it's so unreactive is because of the 6 pi electrons that are delocalized around the ring in the p orbitals. However, arenes are extremely weak nucleophiles, so if we add a very strong electrophile, we can get them to react. The overall process of EAS is that we start with a benzene, react it with a strong electrophile, and that's going to substitute one of the hydrogens on the aromatic ring with that electrophile. The mechanism for all 5 reactions that we learn in this chapter is pretty much following the same pattern, where there's this pre-step to activate the electrophile and then the electrophilic aromatic substitution step itself. In all cases, the EAS reaction is identical. You have one of the alkenes of the benzene ring acting like a nucleophile attacking an electrophile and kicking off usually some sort of leaving group. And then some base, maybe even the leaving group, comes back and restores aromaticity. And the 5 reactions that we're going to learn in this chapter and use in this chapter are halogenation, sulfonation, nitration, alkylation, and acylation. We looked at the halogenation reaction. And the halogenation reaction conditions were from benzene. We treated it with Br2 and an FeBr3 catalyst. You could also swap out chlorine for the bromine. And that's going to add 1 halogen to the ring. We looked at the mechanism. The first step involved that pre-activation where the dibromine reacted with the iron to form this positively charged bromine complex, which was extremely electrophilic. Essentially, this bromine in the middle was going to act as like a very good leaving group. So what happens is then the benzene ring attacks the terminal bromine and kicks off that very good leaving group, enabling us to create the carbon-bromine bond to the benzene ring. That disrupts the aromaticity to give a carbocation intermediate, which is restored by FeBr4 acting as a base, and we show that with the iron-bromine bond acting as the base to grab that proton, and that's going to produce the product alongside HBr and regenerate the FeBr3 catalyst. So this exact mechanism can be totally repeated using chlorine instead of bromine. Just swap out all the Brs with Cls and you're fine. We looked at sulfonation. By treating a benzene ring with SO3 and H2SO4, we create a sulfonic acid. The mechanism, again, we have this pre-step activation where the SO3 is protonated by sulfuric acid to give us a positively charged sulfur. Then the benzene ring attacks the positively charged sulfur to deliver that sulfonic acid, but also create a carbocation, which is reacted with the bisulfate base to restore aromaticity in an acid-base reaction, and that is going to create the sulfonic acid. Here we see nitration. So we have a benzene ring, and that's reacting with nitric acid and sulfuric acid to form nitrobenzene. The mechanism, we have nitric acid getting protonated by sulfuric acid. Interesting that we're going to protonate the neutral oxygen and not the negatively charged oxygen like you might think. That's going to allow us to get to an intermediate where the negatively charged oxygen can push its electrons towards nitrogen, ejecting water as a leaving group and forming the highly electrophilic nitronium ion. The nitronium ion reacts with the benzene ring to give us the disrupted aromaticity species. And then we use water as a base. You could also use the bisulfite anion to restore aromaticity and produce the nitrated product. Then we looked at friedel-crafts alkylation, where we could take a benzene ring and treat that with an alkyl halide in the presence of an aluminum trichloride catalyst to form alkylated benzene. The mechanism of the reaction was slightly different depending on the substitution of the alkyl halide. If the alkyl halide was secondary or tertiary, the reaction proceeded through a carbocation intermediate shown in the mechanism below. If the alkyl halide was primary or methyl, the carbocation intermediate was not formed, and instead we went by this other mechanism that looks a lot more like SN2, where we generate the highly activated chlorine with a positively charged electrophile. The benzene ring does an SN2-like reaction, attacking the alpha carbon and displacing that positively charged chlorine directly without the intermediacy of a carbocation. That just leads to the carbocation intermediate, which is reacted with the aluminum tetrachloride to reform aromaticity and produce the alkylated product. We discussed that there was a major problem with friedel-crafts alkylation, and that it was almost impossible to add just one alkyl group. Because the benzene ring, after the friedel-crafts alkylation reaction, gets a alkyl group added, and because alkyl groups are electron donating groups, with each friedel-crafts alkylation, we make the benzene more electron rich. And since the benzene's acting as a nucleophile, if we make it more electron rich, we're going to make it more reactive. And the result is polyalkylation, and that it's very difficult to add just one methyl group, because once you add the first methyl group, the benzene wants to react again with the alkyl halide and the aluminum trichloride catalyst to add multiple methyl groups to the benzene ring. So we looked then at reaction 5, which is friedel-crafts acylation, where the benzene was reacted with an acid chloride in the presence of aluminum trichloride to give ketone-type products. The mechanism, again, we have that pre-activation step that leads us to the acylium ion, which is our active electrophile. The benzene ring attacks the acylium ion, and then aluminum tetrachloride acts as a base to restore aromaticity and produce a ketone product. And because a ketone is an electron withdrawing group, unlike the electron donating alkyl group, polyalkylation is not a problem with the friedel-crafts acylation. All right, so that's basically catching up to where we're at. And now what we want to discuss is in all of these reactions we looked at, the benzene ring had no existing substituents on it. The benzene ring was totally naked with 6 hydrogens all around it. But we'll see that this reaction can be affected by the existence of a substituent. So here is the overall idea of this part of the lecture. Imagine we had a benzene ring with some attachment abbreviated with R. Okay? And then we did one of those 5 EAS reactions, so I'll abbreviate that by putting an E plus as an electrophile and writing EAS to signify this is an electrophilic aromatic substitution reaction. What you'll see is that there's 3 possible products that could form. We could add the electrophile next to the existing R group. That relationship is called ortho. And this describes a 1-2 relationship between the existing substituent and the new substituent, ortho. We could also form a meta product. Meta is when the substituent is formed in a 1-3 relationship with the existing R group. And then finally, we could have para, where the substituent is added in a 1-4 relationship from that existing R group. Okay? So what we're going to look at is the fact that certain substituents have preference for one or more of these regioisomers. That's what the word we would use to describe these regioisomers. So substituents. They affect the rate of the EAS reaction. I didn't mention that. So the R group can also affect the rate, speed up or slow down EAS. And it can affect the regioselectivity. So let's just go back and recall the mechanism of the EAS reaction really quickly. They'll help us understand how a substituent could potentially have an influence on this. So we'll look back at the mechanism. Here's our benzene ring. And remember that the benzene is nucleophilic, weakly nucleophilic, but it is nucleophilic. So benzene is nucleophilic. And then we're going to add a really strong electrophile. The benzene will attack the electrophile, and that's going to form the carbocation intermediate. Okay, so that's the first step of every EAS reaction. Now, let's see what would happen if we had a pre-existing substituent on the ring. So I'll draw my benzene. I'll put an R group on my benzene. And again, I'll add my electrophile. Okay, here's the benzene attacking the electrophile just like before. And now let's look at this carbocation intermediate. Okay, there's our carbocation intermediate. Now, that pre-existing substituent, that R group, could either stabilize or destabilize that carbocation. That's going to be able to affect the rate of the reaction and the regioselectivity. So here we have a pre-existing substituent. And so the identity of R will matter. And that sort of makes intuitive sense. Imagine R was a really strong electron withdrawing group. That would make the carbocation feel even more positive, and that would slow the reaction down and destabilize the carbocation intermediate. However, if the R group was really electron rich, it could help support the formation of the carbocation by making it not feel so alone and giving it some more electron density. That would increase the rate of the reaction. It could also have influence on regioselectivity. How close do you want to form the carbocation in proximity to a donor or withdrawing group? So, as we've seen before when we were talking about Diels-Alder, there's two types of substituents, donors and withdrawers. There's electron donating groups, which are called activators. Electron donating groups activate the benzene ring towards electrophilic aromatic substitution. They accelerate the rate. They also make the arene more nucleophilic by adding electron density. On the other hand, we also have electron withdrawing groups. These are called deactivators. These deactivating groups are going to slow down EAS. And they're also going to reduce arene nucleophilicity. Okay. So now what I'd like to do is just show you a few of these substituents so that you are aware of what kind of substituents do what. And we're going to classify them by activators or deactivators. So I'll call this the grand list of substituents. And at the very top of our list, we'll add our donor groups or our activating groups. And the first group on our list is alkoxy. Alkoxy group. And I'll draw this little squiggly line to show the point of connection to the benzene ring. An alkoxy group could be something like a methoxy group. Right, and it's got these lone pairs directly attached to the benzene ring. Those lone pairs can donate into the ring their electron density, and that's going to increase the nucleophilicity of the benzene ring. We could also have an amino group. Again, we've got the lone pair on nitrogen that can act as a donor group. We could have hydroxy. Hydroxy is just an OH group. Again, you'll notice there's those lone pairs. You know what, I'm going to stop drawing in the lone pairs. You know they're there. Okay, we have the hydroxy group with its lone pairs. So we're going to classify these three groups as strong activators. And the reason they're called strong activators is because they all have that lone pair on attached heteroatoms, so they're resonance donors. And because they're resonance donors, that makes them strong activators. Okay, let's take a look at another type of activator. It's just an alkyl group. Alkyl group is something like a methyl group attached to a benzene ring, and that we're going to consider as our only weak activator. Now, methyl group, being as that it is a weak activator, just keep in mind that it's not just methyl. It could also be ethyl or phenyl or propyl, right? Any sort of carbon-containing group we're going to classify as a weak activator, and that's because it's an inductive donor. So there's no resonance donation, but it is electron releasing. So we do consider it a weak activator, but not as strong as the strong activators. Next up on our list, we'll have a halo substituent, so halide. This could be something like chloride or bromine or fluoride or something. So I'll just draw chlorine. This substituent is going to be our only weak deactivator. For the halide substituent, it is inductively a withdrawing group. The halogens are usually quite electronegative, so they're going to want to suck electron density out of the ring because they're very selfish and electronegative. And by that virtue, they're going to be deactivating groups. Now, you may say, well, wait a minute. The halogen has lone pairs on it. Can it also be a resonance donor? And wouldn't that overpower its inductive withdrawing power, since resonance typically overpowers inductive effects? And I would say that your analysis is very astute, and that's a really good point. But it turns out they've done experiments, and they found that, strangely enough, the resonance donation ability of halogens is overpowered by their inductive withdrawing ability. So experiments have proven that that is not the case. Okay. Now let's look at a few strong deactivators. We have things like the carbonyl. And carbonyl group could be something like a ketone attached to the ring. That's going to have a resonance effect that sucks electron density out of the ring. Cyano group could be like a CN triple bond, would be a strong withdrawing group. Nitro. An O2 group is a strong withdrawing group. And sulfonyl. That's the SO3H group. And these are all going to be strong resonance withdrawing groups. So these are going to be called strong deactivators. These groups use their resonance abilities to suck extreme amounts of electron density out of the aromatic ring, slowing down EAS tremendously. And I'll put in parentheses here that they do this effect by resonance to differentiate it from another class of strong deactivating groups like the trifluoromethyl group. The trifluoromethyl group, which looks like this, CF3, is a strong deactivating group. And so is the ammonium group. That would be something like NH3+. All right. These are also strong deactivators, but they are inductively strong deactivators. So strong deactivators. They do not have a resonance form that is we can draw that shows the electron density being sucked out, but they do have a very strong withdrawing inductive effect. So they are also classified as strong deactivators. Okay, so now that we have this list of substituents, and you should familiarize yourself with these and memorize each of these substituents and what category they belong into, because you'll see in just a moment that that's going to become very important for our analysis. So it turns out the regioselectivity of EAS can be controlled on the basis of whether the existing substituent on a benzene ring is a strong deactivator or not a strong deactivator. So if you have a strong deactivator on the ring, these are all the electron withdrawing groups, by the way, except for the halide. The halide is a withdrawing group, a deactivating group, but is not a strong deactivator, it's a weak deactivator. And so if you have the strong deactivator on the benzene ring, and you do an EAS reaction, one of the 5 EAS reactions, we are going to get the meta product as the major product. So we are going to add the electrophile group meta to the strong deactivating group. Everything else that is all the electron donating groups, and then also including the halogen. So electron donating groups plus the halogens are going to actually favor the para product. So here we have our benzene ring, and now the R group is something donating, and we do EAS. We're going to actually favor the para product. We do get some ortho as well, quite a bit of ortho. So we would get some ortho plus para. And for the purposes of this class, para is going to be our major product. So let's take a look at an example of how this regioselectivity manifests itself in a EAS reaction. So let's take a benzene ring with a methyl group on it. This is called toluene. And so if we treat that with the halogenation conditions, so Br2, FeBr3, we know this reaction is going to add a bromine to the ring, but where will it add the bromine? Well, the actual experimental results are we will add 40% to the ortho position. Plus, we would get less than 1% of meta. Less than 1% meta. And then we would get 60%, about 60% para. So you can see that the para product is the favored product for this reaction because the methyl group is a electron donating group. Or in other words, the methyl group is not a strong deactivating group, so the para product is the major product. Let's take a look at another example here. Okay, let's take a benzene ring with a sulfonic acid on it. We know that's one of our strong resonance withdrawing groups. And then let's treat that with nitric acid and H2SO4. This is the nitration conditions. So we know this is going to add a NO2 group somewhere to our ring. It turns out that that's going to add it selectively to the meta position. Okay, so we're not going to get any ortho or para in this case. Okay, that's because the sulfonic acid is a strong deactivating group. That's going to drive the EAS reaction to produce a product where the nitro group is meta. Okay, so now in this part of the lecture, now that you've seen the rule, I want to try and rationalize to you why this is occurring. Okay, so let's take a look at a electron-rich aromatic ring. Okay, so here we have a methoxy group on a benzene ring, and you should recognize the methoxy group is a strong resonance activating group. And now we're going to do an EAS reaction. So I'm just going to do a generic EAS reaction and say that we're going to add some electrophile. So now let's look at the carbocation that forms if I add that electrophile ortho. So we're going to do an ortho addition, meaning that we're going to add that new electrophile right next door to the OME group. So here's my OME group, and we're going to add the electrophile right next door. And what I want you to notice is, look at the carbocation that we form when we do that. The carbocation is formed right next to the electron donating OME group, so we can draw a really nice resonance structure where the methoxy group's lone pairs can kick into that carbocation and give us a fantastic resonance structure. The resonance structure is really nice because all the octets are filled. Okay. Now let's look at what happens if we try and add meta. So meta. Okay, so again, here's our benzene ring. Here's our OME group. Okay, so now let's add the substituent to the meta position. Okay, so if we do that, we're going to put the substituent, let's say, down here. Let's put the carbocation over here. Now we've got a little bit of an issue with this carbocation, is that that plus charge cannot be stabilized by the lone pairs on the methoxy group. You can try all you want to draw a resonance structure, but you'll never be able to fill that empty octet. Look, we can try and draw some arrows. Nope, we can't go any further because that would be putting 10 electrons on that carbon. There's no way that we can get electrons to fill that carbocation. That's not a valid resonance structure either. So when you put the substituents ortho and para, you can draw a resonance structure that allows us to satisfy the octet of that carbocation that forms. However, in the meta case, there's no way to push the electrons to stabilize the carbocation. So I'll just say plus charge can't be resonated. I don't know that that is an official word, but so it can't be resonated by the lone pair electrons of our donor group. In other words, we can't get there from here. For practice, why don't you try drawing the para carbocation that would form when you do this reaction and prove to yourself that the lone pairs can reach the carbocation that forms when the electrophile is added to the para position. Okay. So there's another factor, though, that could also explain why the electron donor groups prefer reaction at the ortho and para positions. And that is the electron donating groups increase the nucleophilicity at those positions. And sometimes I'll abbreviate ortho and para as O and P positions. So here we'll look at an example of what I mean by that by drawing some resonance structures. So here I'll again draw methoxybenzene. And now watch, I can draw some resonance structures. So I'll use the lone pairs on the oxygen to push into the benzene ring and start dumping lone pairs on various carbons of the benzene ring. So if I do that, we get this resonance structure. Now, I'm not saying these are very good or major resonance structures, but they are resonance structures. They do exist, right? So they are increasing the the nucleophilicity at that ortho position. We can draw another resonance structure. Now we move that lone pair next to pi bond, can move it to the para position. And we can also move it again to the other ortho position. There's two ortho positions. You can move it on to the left side. Right? So you can see that the electron donating group allows us to put a negative charge at the ortho and para positions, but there's no way to put a negative charge on the meta positions. There's no possible resonance structure that does that. So try as you might, you will not be able to put a negative charge at a meta position. And so this helps explain why the arene becomes more nucleophilic at the ortho and para positions, because it has a greater partial negative charge at that position. And so because it's more nucleophilic at the ortho-para positions, those positions are more likely to attack the electrophile in the EAS reaction. So two factors. One factor explains ortho and para selectivity on the basis of the carbocation intermediates being more stable when ortho and para addition occurs. And another factor talks about before the reaction even occurs, the ortho and para positions have increased nucleophilicity. So these two factors can be used to rationalize why we observe the certain selectivity. Okay, but our analysis would not be complete now if we didn't also discuss the rationalization of why electron withdrawing groups are meta-directors. So the question now we want to answer is why are EWGs meta-directors? And it turns out it's more than just not having the effects that the EDGs have, but actually there is sort of an active hate for the ortho and para positions and a favoritism for the meta positions when an electron withdrawing group is present. Reason number one, ortho-para exhibit partial positive character when electron withdrawing group is present. Remember that by creating partial positive character, we're reducing the nucleophilicity at these positions. Right? So if they exhibit partial plus character, they're less nucleophilic. Let's draw some resonance structures that can explain that. So I'll draw a benzene ring here. And I need to put an electron withdrawing group on it. So I'll put the aldehyde group. And now look what we can do. Electrons from the aromatic ring can be pushed out of the aromatic ring onto the aldehyde oxygen, or any electron withdrawing group that's out there. And look what that's going to create in our resonance form. It's going to create a carbocation at the ortho position. And we can move that carbocation around the ring in other resonance structures. So I'll move that pi bond over, and you can see we can move that positive charge to the para position too. And we can move it to the other ortho position by moving this pi bond. So you can see that the ortho and para positions are made less nucleophilic by the presence of an electron withdrawing group, because there's resonance structures that we can draw that put plus charges on those positions. So this is kind of the opposite of reason number 2 for the electron donating groups, right? So before the reaction even occurs, there is lower nucleophilicity at the ortho-para positions. Thereby, there's going to be a natural favoritism for the meta positions. Okay, now let's take a look at reason number 2, which has to do with the carbocation stability after electrophilic aromatic substitution. So the carbocation can move 3 times when meta, but only 2 times when orthopara. So I'll draw this out and explain this. So carbocation can move after EAS 3 times and never is next to EWG. Okay, so we definitely have to show an example of this, because reading that probably makes no sense, but when you look at the picture, it makes a lot more sense. So here is our same benzene ring. Okay, and what we're going to do is we're going to react one of the alkenes with our electrophile to give us meta product. Okay, so that alkene down there will react. That's going to generate a carbocation right here, and our electrophile is added to the meta position, so meta to our aldehyde. And now we can draw some resonance structures for that carbocation. We can move this pi bond over. Remember, that's pi bond next to MTP. That's a resonance structure that we can draw. We'll move the carbocation up here to the top, and we can draw another resonance structure where this pi bond moves over. So you can see we can really delocalize this positive charge pretty nicely. And we don't have an issue. We can delocalize the positive charge, that stabilizes the positive charge, and so meta addition of our electrophile is really nice because we can delocalize our positive charge in 3 possible ways. Now we want to see, okay, what happens if para EAS occurs? How would that look? So we'll say, what if para occurred? Okay, so let's go ahead and draw I'll draw a benzene ring with a different withdrawing group on it. How about the CF3 group? We know that's a strong deactivator. Okay, now let's add our electrophile, and we're going to make sure we generate the electrophile at the para position, which we know this is going to be a bad example. So we're doing this example to show why this is bad. So here's our CF3 group. Okay, so we added our electrophile to the para position. And so that's going to generate our carbocation at the meta position. Now let's do the same thing. Let's draw some resonance structures. So we can move this pi bond over. Is it just a resonance structure? We're moving that carbocation around. And we draw another resonance structure. Move this pi bond up. And put the carbocation down here now. Okay, so what's the big deal? It looks like we have 3 resonance structures again, but no. Look at this structure right here. Look at where the carbocation is. The carbocation is placed directly next to a strong electron withdrawing group. This carbocation is already electron deficient, and now this resonance structure shows withdrawing even more electron density away from something that's already electron poor. That's terrible. So we should say gross. Carbocation next to electron withdrawing group. And we know that's got to be really bad. But look at the above example. The carbocation, when we add the electrophile in the meta position, is never placed next to the electron withdrawing group. It sneakily avoids being next to that aldehyde in every single resonance structure, but that is never the case if you add the electrophile to the para or ortho positions. So these are 2 reasons why strong electron withdrawing groups strongly favor addition of the next substituent to the meta position, and they avoid actively the ortho and para positions. Okay, so let's take a look at an example of how these sort of rules become practical in synthesis. So let's say I asked you, and this is honestly, this is the part of the class that ends up being like a puzzle, because you have to be smart and choose the order correctly for these reactions. So let me show you a cool example here. So here we have benzene, and let's say I wanted you to provide me a synthesis, so as many steps as you need, but I want this product here. I want the chlorine and a nitro group on my benzene. So it seems that there were 2 reactions that had to be conducted. There had to be a halogenation at some point to put on the chlorine, and there had to be a nitration at some point to put on the nitro group. But the order that we do these reactions is going to matter a lot. So let's see what happens if we do it in one particular order. So let's do the halogenation first. So remember, the halogenation conditions are, for example, Cl2 and FeCl3. And that's just going to put a chlorine on our ring. And we can put that first chlorine anywhere we want. Remember, the molecule is totally symmetric, so any position you put it on is going to be equivalent. So I'll just put it at the top because I know that's kind of where we want it in the way the product's drawn. And then let's do our nitration reaction second. So HNO3 is our nitric acid with H2SO4. Okay, now we need to inspect our substituent and decide, okay, what kind of substituent is that? Is it a strong withdrawing group or not? And the chlorine is a weak deactivating group. So it's not a strong withdrawing group. It's not a strong deactivator. It's a weak deactivator. And weak deactivators favor the para position as the major product. Okay? So what that means is that because we have that chlorine, now we're going to add our nitro group to the para position selectively. So this works. This order is good, and we're getting the correct product using this order. But now let's look at the example. If we did the nitration first, what would happen? So here's our benzene ring, and I'll do the HNO3, H2SO4. Okay, now we can put the nitro group wherever we want, so I'll just put it on the bottom since that's kind of where it's drawn in the product. And now I'll do the halogenation reaction. So Cl2, FeCl3. But now the substituent on our benzene ring is a strong deactivating group. It's the nitro group, which is a strong deactivating group. That's going to push the next reaction to the meta position. So this will not lead to the correct product. It will put the chlorine at one of the meta positions. Okay, So this order above, where we did halogenation followed by nitration, was correct. But if we did nitration first followed by halogenation, we got the wrong regioisomer. Okay, so you're going to see this is a very simple example, but I'm going to create puzzles for you where you have to do the reaction, maybe adding not just one, not just two, but three substituents in a particular order. It's going to be a lot like a puzzle. Okay, so that's where we're going with this. So you'll see that it's just 5 reactions in this chapter, but the way that we use the reactions and the order that we use the reactions is going to have a big impact on whether you get the right answer or not. Okay?